So what is a network topology here? Let us see. So the network topology is a graphical representation of electrical circuits. Right here, you are given one electrical circuit. That electrical circuit you have to represent in a graphical notation, and this will helpful for analyzing the complex electrical circuit. So by converting them into the network graphs, the network topology is also called as the graph theory. Okay, so this graph theory mainly used for solving complex electric circuits, right? So as we know, the nodal analysis, mesh analysis. So these methods we can use for only simple networks, right? So if you are having only 3 nodal equations, you can solve. If you are having 4, you can solve. So, but if the number of equations are increasing, it is not possible to use those KCL or KVL, and at the same time nodal analysis and mesh analysis. Those methods will not be helpful for solving the complex circuit. So we will use the graph theory. Okay. But here the graph or network graph. So it is the pictorial representation of an electrical network. So on this electrical network will consisting of a set of nodes which are connected by the branches. And this electrical network or circuit can be converted into its equivalent graph just by replacing the passive elements like resistors, inductors, and capacitors, and other active elements, voltage sources or current sources. So with branches or with a single line segment. If you're having the passive elements here is nothing but resistor, inductor, and capacitor. Those will be just replaced by one line. Okay. So then voltage source will be short circuited and current sources will be open circuited. Okay. So the line segment, in the graph represents the branch which is corresponding to either passive elements or voltage sources of the electrical network. And the vertices of the graph will represent the nodes. Okay. Now, if you take one simple example, here let us see here. This is the electrical network. So now this electrical network we are going to represent in a graphical manner. Okay. This is the electrical network, and this is the equivalent graph for this electrical network. Right here, you are having only the resistors. Right. So all the resistances here can be represented by line segments like this. Okay, this 30 ohm will be represented by the line segment A. Okay, and this 5 ohms will be represented by the line segment B, and 10 ohms is represented with line segment C, and these 10 ohms will be represented by line segment BCE, and this voltage source 20 volt sources is represented by this line segment D, and this 20 volts will be represented by line segment F, and this current source will be open circuited. Okay, so while transforming an electrical network to equivalent graph, so all the passive elements, either resistors, inductors, or capacitors, those will be replaced by line segments, and voltage sources will be short circuited, and those also represented by line segment, but the current sources will be open circuited, right? So then for this electrical network, you will get the unequivalent graph will be like this. Here the nodes will represent. Hello? Okay, 5 minutes now. Inspection team is coming. I will join again.
अन्नी का फिर
Halo.
So, okay, right now. So here we are discussing the network topology. So in the network topology, simply, so an electrical network will be replaced by an equivalent graph. Okay, right? While converting an electrical network into an equivalent graph, all the nodes are represented with the vertices of your graph. 1, 2, 3, and 4. All the four nodes will be called as vertices in the equivalent graph. And these passive elements, all the resistors, if there are any inductors, those inductors, if there are any capacitors, those capacitors. Okay, all the passive elements will be represented by line segment between the vertices. Right here, between 1 and 3 nodes, you are having the 30 ohm resistance. Now this 30 ohm resistance is represented as a line segment between the same 1 and 3. Okay, similarly, so 5 ohms resistance which is between 1 and 2 nodes will be represented by a line segment B here between the same 1 and 2 vertices. Okay, like this, all the passive elements will be represented by line segment. And if there are any voltage sources, those voltage sources are short circuited, and again they are represented like a line segment. Between 1 and 4, you have the voltage source, right? So this voltage source also will be represented as one line segment by short circuiting the voltage source. And if there are any current sources, those current sources are open circuited, and those current sources will not be represented on the graph. So if you see here, between these 4 and 3, you are having a 20 ohms. That 20 ohm is represented with one line segment EF. So, but this current source is not represented with any line segment. Okay, so this is how you can draw the equivalent graph from the given electrical network, right? So now, if you see the number of nodes present in the graph, so this number of nodes present in the graph will be equal to the number of principal nodes present in the electrical circuit. Principal nodes here is nothing but independent nodes, you can say. Okay, so where 3 or more elements are connected, right? So after converting an electrical network into an equivalent graph, you will get the same number of nodes here in the graph also. Okay, so the number of nodes or vertices, you can say, in the graph, those will be the same as the principal nodes or independent nodes which are present in the electrical circuit. So, but if you observe the branches, number of branches which are present in the equivalent graph, so those branches are less than or equal to the number of branches present in the electrical circuit, right? So if you see here, the electrical circuit is having a total of how many branches? So this is one branch, this is one branch, 2, 3, 4, 5, 6, 7. 7 branches are there in this electrical network. So along with your current source also. So, but when coming to the equivalent graph of this network, you are having only 6 branches. Okay, so the number of branches which are present in the graph will be less than or sometimes equal to the number of branches present in the electrical circuit. Why? So, right, why? Because the electrical current sources which are in the electrical network will be replaced by open circuit in the graph, so that branch will not be reflected in the graph. So you will be having less number of or equal number of branches in the electrical equivalent graph. Okay, right. So if you see the graph terminology or graphs, some definitions which you will come across the graph theory. So these are the definition. So element, the first one is the element, right? If you see the element is nothing but in each network element, so which is replaced by the line segment or an arc while constructing a graph is called the element here, right? So while drawing an electrical graph here, sorry. So while drawing the graph here, we are representing these branches or elements of your electrical network into a line segment or like an arc. Okay, so these are called the elements here. Okay, so those electrical elements are represented by line segments or arcs in the equivalent graph. Okay, each line segment or arc in the graph is called the element. Okay, so now what is the node and vertex, right? Node or vertex, both are the same, right? So it is the point where 3 or more branches are connected together, you can say, right? So if there are 3 or more elements are connected, so a terminal which is where more elements are connected, that element is called the node here. Okay, or that point is called the node. So that node you can even call it as a vertex also. And you have the edge. So the edge is nothing but an element of each graph. You can call it as an edge here. So what is element? Okay, it is a line segment or an arc in the graph, right? So each line segment is called one edge of the graph. So then path. So path is nothing but it is the set of elements which are connected together such that not more than 2 elements are connected to any node, right? Here while drawing the path, so there should not be more than 2 elements which are connected to the same node. Okay. So what is closed path or loop? Okay. So closed path or loop is nothing but it is the set of elements traverse and starting from one node to and returning from the same node, right? So if you see here this graph here, right? So now if you take this node and by starting from this node and traversing through different nodes, and if you are coming to the same node again, so now this is called one loop here. Okay, so loop, or you can even call it as a closed path. Okay, so while traversing from one node to towards the some other nodes and coming to the same node, so it should not pass through any node 2 times. Only one time only it has to pass. Okay, so now here if you start again, you can even go through this element A, then F, then D. So like this. So this is also one loop or closed path, you can say. Okay, right. So then what is the degree of the node? Right, this degree of the node is nothing but number of edges, so which are connected to a node or vertex is called the degree of the graph, right? So now if you see the same example before, how many elements are connected to a particular node? So the number of edges which are connected to the node, it is called the degree of the graph. And rank of the graph is this value will be 1 less than the principal nodes. Okay, so if you are having n number of nodes, and the rank of the graph will be n minus 1. Okay, so these definitions you will come across while analyzing the networks using the graph theory. Right, what are the different types of graphs which are present in the graph theory or network topology? Right, so first one is the connected graph. Okay, so connected graph, if there exists at least one branch, so between any 2 nodes of a graph, then it is called the connected graph. Right, if you are having a number of nodes, n number of nodes, right, now at least between any 2 nodes there must be one element. Okay, so if you see this diagram, the first diagram here, so if you see 1 and 3, so between 1 and 3 you have the element A. So between 1 and 2 you have the element B. Between 2 and 3 you have the element C. Between 1 and 4 you have the element D. Okay, so like that, so at least one branch must be present between any 2 nodes of the graph. So then you can say that this graph is a connected graph. Then what is unconnected graph? Unconnected graph is nothing but if at least one node in the graph is not connected to any one single branch. So then you can say that graph is called the unconnected graph. So if you observe the second figure, right? So now between the first node here, between first node to any other node, you are not having any element, or you are not having any single branch also. So you can say that this type of graph is a unconnected graph. Okay, so in unconnected graph, at least one node in the graph must be remain unconnected by even a single branch. Okay, so then what is undirected or unoriented graph? Okay, next classification is the undirected graph or unoriented graph. So if the branches of a graph are not represented with arrows, okay, so direction of current, so then you can say that the graph is a undirected graph. If you see the third diagram here, right, so between 1 and 3 how the direction of current is flowing, so it is not represented here, right? So in this graph between if you observe any branch, so the direction of current is not represented here. Okay, so these type of graphs are called the undirected graphs or unoriented graphs. right? So then what is directed or oriented graph? So in directed and oriented graph, you will represent the direction of currents with arrows. Okay, if you see the fourth figure here, right? So for all the branches, if you observe all the branches, the direction is represented here with the arrows here. Okay. So now, if all the branches are represented with some arrows, so then these type of graphs are called the oriented graphs, or you can even call it as a directed graph. So these are the different types of the graphs. Okay, connected graph, unconnected graph, oriented graph, and unoriented graph. Right. So in a connected graph, there must be at least one single branch between any two nodes in the graph. So, but if you see the unconnected graph, so there will be no element between any at least one pair of nodes. Okay, if you see the node 1 and 2, so there is no element, right? So now here at least one node is single here. So one node is not connected to any other node with any branches. So such type of graphs are called the unconnected graph. And in oriented graph, you are having the direction of currents in all the branches. But in unoriented graph, those directions are not represented. Okay, so directions are represented by arrows in oriented graph, right? But in unoriented graph, those directions will not be represented. So then, what is planar and what is non-planar graphs, right? So if you draw a graph on the plane surface, so then there should not be any crossovers. Right, in such a case, that graph is said to be a planar graph. Okay, if you draw the network with a graph on a plain paper, and if you are observing some crossovers, so then it's in such a case you can say that that graph is a non-planar graph. So what one? Can you show the circuit diagram for second one? Which one?
For the unconnected graph, sir.
Unconnected graph. So unconnected graph is nothing but here if you take one node here, the nodes name 1, 2, 3, 4. These are the total number of nodes which are there in the graph. So, but if you observe here, so between 1 and 2, you are not having any branch. Okay, this node is not connected with any other nodes. Okay, so those such type of graphs are called the unconnected graphs.
So can you draw the circuit diagram for this thing?
The equivalent circuit diagram you are asking.
Yes, sir.
Okay, so for this same I will draw. So here you are having one current source, right? Here also you are having one current source. Okay, so then here you are having one element. Here you are having one element, and here you are having one element like this. Okay. So,
Thank you, sir.
So now here, even here, if you are taking the voltage source, suppose if the voltage source is there here between this 1 and 2, so now there is a branch connected between these two. In such a case, it will become again connected graph only. Okay, if your node is not connected with any other nodes and it is single after drawing the graph from equivalent circuit, so then in such a case that graph is called the unconnected graph. Okay, so generally for general electrical network, you may not get unconnected graphs, but so while drawing the subgraphs, so then you will get these unconnected graphs. I will tell you how you can draw the subgraphs. Okay. Right, I think non-planar and planar is completed, right? If you draw the graph on a plain paper, if there are no crossovers, you can say that that graph is a planar graph. If there are any crossovers, then you can say that that graph is a non-planar graph. If you observe the figures, you can get the clarity. So in first graph, we are not having any crossovers. So, but for the second graph, you are having here one crossover. Okay, so this is the crossover here. Okay, so this graph is a non-planar graph, and this graph is a planar graph. Right. So then, what is subgraph and what are the types of it? Okay, So now a subgraph is nothing but it is a part of the graph. Okay. So now if you remove some nodes or some branches from the given graph, so generally you will get one subgraph. Okay. So here in the previous example, you are having a graph like this. Suppose if you are having a graph like this. Now I'm removing this branch and this branch, so that you are getting this one. Okay, now you can say that this graph is a subgraph for this main graph. Okay, so subgraph is a part of the graph, and this subgraph you will get if you remove some nodes and branches from the given main graph. Okay, so the number of branches and the number of nodes in subgraph will be generally less than the original graph. Hence, we can conclude that so the subgraph is nothing but it is a subset of the main graph. And if you observe the classifications of this subgraph, so there will be mainly two classifications are there. So one classification is called the tree, and another one is called the co-tree. Okay. So now what is tree here? Right. So tree is a connected subgraph. Okay. So you know what is connected graph, right? So in connected graph, all the nodes must be connected, right? That means there must be at least one single branch between any two pairs of nodes, right? So between any two pairs of node, if you take, then at least one single branch must be presented. Then in such a case, you can say that it is called a connected graph. Right now, here the tree, so which is a subgraph of main graph. Okay, so this is also a connected graph. So tree is a connected subgraph for the given graph, which contains all the nodes of a graph. So, but there should not be any closed loop. Okay, so now if you take all the nodes in the main graph, and if you draw a subgraph from that graph, so by considering all the nodes and without any loop, so then in such a case that subgraph is called the tree. Okay, so for the same example again here, for the same example, so which is this one. Okay, here you are having nodes 1, 2, 3, 4 nodes are there in the main graph, right? All the nodes must be presented here also. 1, 2, 3, and 4. All the nodes are there. So, but if you see here, there is no closed path is there. Okay, so we are taking DEF element, DEF branches only, and we are removing this branch, and this branch. Right, after removing this branch, you will get one graph which is called the subgraph. Now, in that subgraph, if you are having all the nodes of the main graph, in such a case, you can say that that subgraph is called a tree. Okay. So now, generally, the branches of this tree are called the twigs. Now here, D, E, F are the twigs of your tree. Okay. So in a tree, you will be having all the nodes which are present in the main graph. Okay, and it is also a connected subgraph, and the branches in that this tree are called the twigs. Okay. So now here the number of branches present in the tree, if you observe, so those should be equal to n minus 1, right? So if you are having n number of nodes, so then if you observe the number of twigs or number of branches in the tree, so then those will be 1 less than the number of nodes. Okay, so here in this tree you are having a total of 4 nodes, right? So if you subtract 1 from here, you will get total number of branches, which is equal to 3, right? Total number of branches, or you can even call it as twigs. Okay, in a tree the branches are called twigs, remember it. Okay, right. Now here this tree is formed by removing this branch, and this branch. Now with all the removed branches, again if you form a subgraph, so that subgraph is called the co-tree. Okay, so co-tree here. Okay, co-tree is a subgraph, so which is formed with the branches that are removed while forming a tree, right? So while forming a tree, we were removed some of the branches. Okay, now in a co-tree, you have to take those removed branches. Okay, and you form another subgraph. So that subgraph is called the code tree. Okay, so generally it is called the complement of a tree, and the branches of this code tree are called the links or chords. Okay, so branches of this code tree is called links or chords, right? So every tree, if you observe, so every tree will be having a corresponding code tree. Okay, so why? Because for forming a tree, you need to take all the nodes and you have to remove some of the branches from the main graph, such that no closed loop will be present. Okay, so now with removed branches, if you draw another subgraph, that graph is called simply code tree. Now in code tree, generally the branches are represented with these dotted lines. Okay, so now here A, B, C. So these are the branches of your code tree. So those are represented with dotted lines. And generally these branches are called the links here in the code tree. Okay. So now if you observe the number of branches which are present in the code tree, so this will be equal to, so difference between the total number of branches in a given main graph and the number of twigs. Okay, so number of links L will be equal to, so total number of branches. So the difference of total number of branches minus number of twigs. Total number of twigs will be, so twigs is nothing but total number of branches in a tree, which is equal to n minus 1. So if you subtract b minus total number of twigs, so then you will get the links, total number of links. L is equal to b minus n plus 1 you will get. So this formula you have to remember. Okay, so for a tree, if you observe, for a tree, the total number of branches, so which are called the twigs, will be equal to n minus 1. Okay, this tree is, if you are having b branches in the main graph, so if you are having b branches in the main graph, now in a tree you will be having n minus 1 branches. Now if you subtract these two, so the remaining branches will be the branches of your code tree. So b minus n minus 1. So this will be the total number of links or total number of branches in a code tree, you can say. Okay. Right, ma'am. So it is already time up. So this incidence matrix we will discuss tomorrow.
Thank you, sir.
Okay, I am stopping here. Thank you.